Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. This problem is an application of Ampere's law. So, we have something like this. We have a current carrying wire that's going to be pretty thin. I'm going to draw it thick, but it's an exaggeration. It's going to be pretty thin compared to everything else. And let's say that it's carrying a current upward like this. We know from the right-hand rule, and just from learning about current carrying wires, that it's going to create a circular magnetic field that's going to vary in magnitude as you go away from the wire. But ultimately, around the wire, circular magnetic fields are being created. Now, what Ampere's law tells us, right, is that if we sum up the parts of the magnetic field that are parallel to the little bits of distance that we travel around the circle, so say we're going to travel around this entire circle along some path like this, but if we then take the parts of the magnetic field that are along that direction and then compare it, and then you take the parts of the magnetic field that are parallel to these little changes, little distances, delta L, that we travel, and multiply them together, add those up all the way around the circle, and that's going to tell us something about the amount of current that is being carried by any wires that enclose the circles that we draw. So if we basically take up all the contributions of the magnetic field that are parallel to the Amperian loop that we draw around any of our current wires, that's going to equal to mu naught, one of our fundamental constants, times all of the currents enclosed in that loop. That's why I put ENC for enclosed by that loop. We saw for a current carrying wire, infinitely long current carrying wire, that Ampere's law can help give us the amount of magnetic field being created at any distance away from that wire. Now, what we're going to do is do the same thing. We're going to see here, right, that the magnetic field will be circular. So the magnetic field is always going to be parallel to a circular loop around this wire. And so that this magnetic field can come out of our sum, and we're going to sum up all of the little lengths that we travel around our circle. And of course, if we add up all the little lengths and travel around our circle, we're going to travel all the way around the entire circumference of the circle, and this summation of all the delta L's becomes the total circumference of our circle. Oops, let me write that better. Current enclosed. So what we see is that the magnetic field given by a current carrying wire is going to be mu naught times the enclosed, all the enclosed currents divided by how far away we are, how big is our loop that we've drawn around this thing. So this problem basically tells us, instead of just having one wire there, what we're going to do is put another wire, I'll just draw it as green, really close to it. So again, I'm exaggerating the distance, but really it's just going to be a thin wire that's very thin compared to, say, the distance r that we have drawn our loop, right? How far away we are from our wire. It's going to be very thin. And depending on which way the current is, it's going to change the magnetic field that is a distance r away from our original wire. So how do we figure out what the new magnetic field is going to be if we have a wire put next to our other one at different different directions of current? Well, let's think about it. So if we put a current in this green wire and we say, let's say we want it to go up as well. So we have a current inside the green wire going up, then it's going to have the current in the same direction as the current from before. Well, if they're going in the same direction, then when we think about the current enclosed here, it's going to be the sum of these, right? So we're going to add these currents up because they're going in the same direction. So ultimately, when we calculate the magnetic field created by these two wires when the current goes in the same direction, right, we take mu naught. We're going to take the current that was there before, add it to the other current and then divide by how far away, 2 pi, and then how far away we care to look from the wires to see how large the magnetic field is. It says in the problem that we care about a distance that is 0.72 meters away. But we'll just call it R for now. So when the currents go in the same direction, we add them together. So mu naught is 4 pi times 10 to the negative 7 Tesla meter per amp. We're going to plug in the summation of both of the currents. The initial current in wire 1 was 12 amps. 12 amps. And then the current in the second wire was 28 amps. So we plug that in. Then we divide by how far away we are from the wires, and then it's 0.72 meters. So put that in my calculator, add the currents together because they're in the same direction. We end up getting that magnetic field is about 1.1 times 10 to the 1.11 times 10 to the negative 5 Teslas. Now, what if the currents are in opposite directions? Well, as you might imagine, if the currents are in opposite directions, we need to subtract them instead. So let's just do that now. So let's plug in what we know, mu naught. Let's write it out. So we have 4 pi times 10 to the negative 7 Tesla meters per amp. And then we're going to multiply by that, the difference between the two. Now, since we just want a magnitude of the magnetic field, let's just take the difference such that it's positive. So we have 28 amps minus 12 amps. And then again, all of this is going to be divided by 2 pi times 0.72 meters. Put that in our calculator, and we see that we get an answer of 4.4 times 10 to the negative 6 Teslas. And that's our answer.